Here we go. Thank you for waiting. Thank you, everyone. Welcome to this session. Today is our first official deep dive session where we will try to tackle a specific topic, trying to understand better something that's related to Skylight that may be useful for our users. My name is Natalie. I think all of you know me here, but I asked a colleague of mine to join because he has expertise in so many things. And so I'd like to introduce my colleague Joe here. Joe, would you like to introduce yourself and share a second of your background?
Sure. My name is Joe Ferdinando. I am the product manager for Skylight. I am a veteran of the United States Coast Guard. And since I departed, I got a degree in computer science from Cornell. So hopefully I can help answer any questions you have about artificial intelligence and how it applies to the maritime domain, and specifically what we do with satellite data. It's great to be here with all of you today.
Thank you, Joe. And thank you, everyone, for joining and for investing your precious time in understanding more about what we do and why we do it. So we're really happy to have you all here. Our goals for this session today is to give you some clear understanding on basic AI concepts. We usually refer to artificial intelligence as AI. So you will probably hear us saying AI all the time, which is shorter and simpler. We also we will try to recognize the opportunities and the challenges that using and implementing AI can pose for us. And also, I will then give the word to Joe, and he will explain how Skylight is integrating AI in helping and enhancing the way we understand what's going on out there on the ocean, right? So we will also share a bit of how our models work and how they perform and how can we trust them, right? That's the goal for today. We will assume, and I know this is the case with the audience we have today, that you have some understanding of what Skylight does and how we work. So we are assuming that you understand the fundamentals for today. We will not go over specific events, but we will try to explain why we work with these events, okay? I have started a session of Q&A, so if you look at the right bottom of your screen, you will see a square, triangle, and a circle. There you will find a section that says Q&A, and you can ask questions also. At the end of the session, we will try to address all these questions in order, right? That's the goal. So I will share some details about what we do and why we do it, right? We are part of the Allen Institute for Artificial Intelligence. We are a nonprofit organization that's a research institute that has a deep knowledge of AI, and it's home for a lot of world-class AI engineers. So we have a specific department that's called Applied Science Team that has several programs that are working with AI to help with conservation in the world. Skylight is one of these initiatives, but we have others that are focusing on other Earth problems. So I will move then to explain why we do this in Skylight. Our core mission is to fight illegal fishing. And illegal fishing is certainly making the ocean the world's largest crime scene, right? So for such a big problem, we need big solutions as well. And so Skylight is analyzing over 10 million square kilometers and processing around, I would say, over 100 million GPS messages every day. and we cover half of the world's EECs weekly, which means we're processing huge, humongous amounts of data, and we try to deliver that in a simple way. So imagine how long it would take to a maritime analyst to identify vessels engaging in different activities, for example, fishing or trash shipments, right? These are all the AIS tracks that we have available in a particular area, but Skylight is giving you the opportunity to digest this pretty easily by just reporting specific events, right? And how do we do that? We use some rules, but we also use artificial intelligence. And that's what we're going to tackle today. One big important disclaimer that we also want to share with you today is that AI is meant to enhance, to complement and facilitate human intervention on maritime surveillance and control. But we are not meant to replace human understanding, the human intelligence, right? We want to save time, we want to make things better, but we do not want to replace and we don't want to remove a human in the loop, right? So this is very important to always remember our goal and to understand how AI can help, but also understand the limitations that it has. And we will also discuss this a little later. So what's AI, right? This is a concept that's pretty trendy these days. We are used to hear this expression or this concept a lot. But what it actually means is pretty simple, right? It's computers performing human activities, right? Emulating human intelligence and doing activities that we could be doing. And sometimes that means that the computers can do it in a more efficient way with different limitations and with bigger opportunities also. So what's the difference between AI and machine learning? As I said, AI is computers doing things that we do, but machine learning is a subset of that that's focusing on the learning process that the computer has and focuses from a technical point of view on the development of algorithms, right? And that's basically what we do in Skylight and what we do at AI2, right? So let me explain a bit more about how the computer learns compared to the traditional programming, right? So what you're seeing here on your screen, this is a human because this will represent human intervention. When we talk about traditional programming, we are telling the computer and we are giving the computer a rule, right? So a human will give the computer a rule and a logic to follow. And then we will give the computer an input and the computer will process this data and will give us an output, which is an answer, right? And this is pretty logical sometimes. So for example, if I will take an example of what we do in Skylight, right? We have speed range events, right? So we give the computer a rule that we want the computer to follow. And we will say, every time there is a vessel transiting below 4 knots in this area, I would like, so this is the rule and the logic, I'd like you to tell me that this is a speed range event. This is relevant for me, right? Then the input that will give the computer is AIS tracks. The computer has already the rules and the logic and will give us the output, which is the speed range event, right? This is pretty straightforward. However, machine learning and AI works completely different, and that's what we want to understand today. Machine learning will create its own pattern. It will create its own rules and logic. So we, as humans, will intervene here. We will give the computer an input, but we also will give an output, right? So we will give input and output to the computer that will create rules and logic, which we call a model. And then the computer will use it to apply it in different situations. And in the future, we would be able to just give an input and the computer will give us an output, okay? This might seem complicated, but it's pretty simple. We will tackle this with an example and you will quickly understand. So I will give the computer, so we're trying to build a model to identify color red, right? This is the example. We try to identify color red. We want the computer to be able to tell me when something is red, right? So how do we train the model? We will give pairs of data, input and output. We will give it a strawberry, for example, and we'll say, that's red, right? That's the pair of data that we will give. Then we will give this picture of a red car and we will say, this is red. We will give the expected output. The same with this flower, but we do this thousands and thousands of times, right? It's not 3 times. It's a lot of data that we need to feed into the model, right? And then the computer will eventually create an AI model with some level of understanding of what the color red is, right? If I asked you to define color red, probably you wouldn't be able to do it. I certainly cannot do it, right? If I'm asked to define color red, I would probably point to red stuff, right? And that's exactly how AI works for this model in particular. But in general, AI will not create a specific rule that works in the same way traditional programming works, where we would have specific rules and identification of the activities that the computer is performing, but it's a model that we can adapt and correct, of course, but it's an abstract concept, right? So if we give enough data and enough pairs of input and output, the computer will create this understanding. So we will, in the future, we will be able to give an input to the computer, and the computer will give us an output. So if you pay attention to this arrow has changed direction. So we don't need to give outputs anymore. Once the computer is trained, we will have the output. The computer will be able to perform the task by itself because it has created a model. So we, in this example, I would be able to give this picture of an apple, and I can ask the computer, is this red? And the computer will be able to say, yeah, this is red, right? But there are some considerations, right? There are some things that we need to take into consideration when we talk about computer understanding and data applications. And that's what we want to discuss today also. So the model will learn from the data we provide, right? So if we have flaws and biases, the computer will replicate that, right? What you're seeing here on this picture is a person, and let's say these are examples of color blindness, right? So you have normal vision and you provide the computer with normal vision examples. This is perfect. The computer will be able to replicate a good model, right? To create a good model. But let's say that I'm colorblind and I'm not able to identify the data correctly, then the computer will learn and will be confused again. So that's very important to keep in mind. The data has to be high quality data that we trust, so that the model can learn from that. And you need to keep in mind that it might not work in the future. Let's say in the future, we change the way we refer to color red. Let's say we don't like color red anymore as a society, and we say, hey, we don't want to call this red. We want to call this pink or dark pink. I don't know. That will mean that the model will no longer be useful for what we want to identify, because the model was trained on color red. So it will keep identifying that color as red, right? So if for specifically coming to Skylight, if the fishing activity in the future changes because we change the way we fish, we will need to retrain our model, right? It's very important also to mention that the model requires a very large amount of data. I've mentioned this before, it's never enough to undergo training. It's very important to have a large data set and a high quality data set. So the model will not find a solution immediately, but eventually over time with training, we'll find it. So it takes time, it takes a lot of effort to be able to train a model and to trust a model. And as I said before, the model will not generate a rule that we can perfectly understand with our human brains, but it will construct a model that's more abstract that we are used to work with, right? And why is this important for understanding maritime activity and for maritime domain awareness? AI will give us the opportunity to work differently and work more efficiently, right? So we can upscale and process bigger data sets and build better and more advanced analytical capabilities, right? We can also react in shorter time. This will give us a better reactivity. We can also find, through AI, we can find new insights, so new relationships or patterns that we as humans may not be able to identify. And also, if we do all this correctly, we can be more cost efficient. This will save us time and money, right? What's very important to highlight here that AI is not meant to be in everywhere or in every simple process, right? There are things that are better than with simple processes or simple rules. So for example, let's take speed range as an example. Speed range events. Oh, I'm sorry, I'm going to mute you. Okay. So speed range events they are created with a simple rule, right? And they work and they are very useful in that way, right? I'm seeing here our friend Andrea from Grenada's Fishery. And for example, they have been able to identify some activity through speed range events in their EEC. However, the fishing model was not able to identify some of these activities, right? Because the AI model is more complex, and sometimes that means that we can identify things that are beyond our understanding, which is great, but sometimes that can also mean that there are some things that will fall off. So in this case, having a simple rule is also helpful to complement the understanding. And as I said before, creating a model, training a model, and upkeeping a model is really hard. It's really expensive, and it's worth it, but it takes a lot of effort. So before getting on board on an AI project, it's always important to consider, is any of these goals that we have here what we are looking for? The answer is yes. Certainly AI can help, but if sometimes we need something simpler, maybe AI is not the answer for that, okay? So that's a message important to convey today. And I think that's it. I'm going to pass it to Joe, who will share with you how Skylight is applying AI for MDA and what we are doing daily in our team.
Nazi, I wonder if do you want to field this question from Gambia Navy before we go on?
Sorry, I missed that. I'm sorry. Yes, please go ahead.
That's okay
People
as well. We
from,
can.
yeah.
Yeah. From Gambia Navy, do you have a question? We see your hand raised. We'll go on otherwise. Okay, yeah, well, let's continue, and we'll definitely have time for discussion and questions at the end of the session. So, thank you, Nati, for covering sort of an overview of what AI is in general. So we're going to talk specifically about what we at Skylight do with AI and how it impacts what you end up seeing on the map and on the application. So next, we have two major things that we use AI for that you end up seeing on the map. It's for analyzing AIS messages and for analyzing satellite imagery. So not to mention earlier that Skylight looks at about 100 million AIS messages every day. That's sent by about 300,000 ships throughout the world at any given time. So that's a lot of ships to watch manually. It would be almost impossible to do for a human to watch all those ships 24/7 to see their behavior. We also deal with massive amounts of satellite imagery, and we'll show you some examples in a few slides of. I see. Okay, yeah, great. Glad you can see our screen now. We have massive amounts of satellite imagery that we process. It would be extremely difficult or impossible for humans to look through it for boats as it becomes available to us. So we use AI to do both of those tasks better. First, we're going to talk about modeling on AI, on AIS, excuse me. So on the next slide, what we do is we train AI models to look for certain behavior in AIS tracks, and it always needs to be something that a human could observe too. At the moment, models can't, they're not magic. A human needs to be capable of doing the task, but if a human can do the task well, then we can use that human to train the computer to do that task well. So next, specifically, how we do this is by having humans do that task. So we set up a system here, and you're seeing a quick example where we look at the entire track of a ship on AIS. A human can select portions of that track and say they were, say, transiting, they were fishing, they were anchored. And this is also very important because, as I'm sure many of you have seen by now, AIS users do not accurately report what they are doing on AIS, even though they can. It's not always accurate, the particular activity. And so we're essentially using humans to correct that and label those AIS messages in a way that the machine can learn from them and learn that particular activity. So right here, we're selecting a portion of the track that's transiting. Once we have a large amount of that data labeled by experts that we trust to do this job and do it very consistently, we then provide it to a model. And when we provide it to the model, it goes through a process called training, which is very time intensive. Through a lot of trial and error, we give it those inputs, in this case, the AIS tracks, and we give it the outputs, in this case, what behavior we want it to learn that track is. So say like, this is an AIS track, and this is it's transiting during this time. That would be hard to write rules for that work in every single circumstance, because you might say, well, we could make a rule based on speed, but that's not always the case, right? Like sometimes vessels are transiting at lots of different speeds, depending on the size of the vessel, etc. You might say for fishing, like, well, if they're going slow and they turn, but that also describes other types of activities, say like surveying or dredging. And so since there's a lot of complicated rules, we allow the machine, the computer, to arrive at the conclusions that work in a lot of cases, because it would take us even more time and effort as humans to come up with rules that work in every single situation. So we put it through this training process of trial and error until it gets better and better and better at coming to the right conclusions. It actually generates a thing called weights in that process, and weights tell the computer how to route the inputs through to get to the right output, almost like navigating its way through city streets. It tells it which turns to make until it arrives at the right location, and you do that through trial and error. And then once we have all those weights in place, we freeze the model, it's done learning, and we can then put in inputs, and now the model has all the rules it needs to make those turns down the correct city streets to arrive at the correct conclusion most of the time. Here's a more detailed example of the annotation process. So we're looking at a track of a ship on AIS over the period of a month. Very complicated, very hard to do manually. So the human is isolating a particular time on this track. They're selecting it, and they're labeling it as long line fishing. And this is a pretty clear example where they go back and forth along a path. So it's a pretty relatively easy example for the computer to learn. But again, very difficult if you had to describe exactly how that's working in, say, a set of rules, like they turned north and then they turned west and then they turned south. And that won't always be true in every case. So we use this trained model to generate the fishing events you see in the platform every day. So rather than having to look through all the tracks manually, you end up seeing the end result of the model output, where it marks a location where a vessel has been detected following a track that looks like fishing. And there are many reasons that a ship could be following that track. And that's where it comes down to you as the human operator to decide, was the model right or wrong? But this is helping you sift through all of that data rather than having to do it yourself. It points you at particular events that are worth paying attention to. We also use something called computer vision, which is a type of machine learning, to look at satellite images, and actually works in an extremely similar way. We give inputs to the computer in a way, actually kind of, as I said, sort of very similar to, we make them sort of look like AIS tracks. We stretch out the images and we give that information. And then we also tell the computer where humans have found boats in those images. And we then allow it to go through a process of trial and error to learn what that means a boat looks like. What does it mean the boat itself looks like? What typically is around a boat when it's been located? This is so critical because these satellite images are really massive and they're being delivered to Skylight 24/7. These are all publicly available images, but what we can do, because we have the AI system in place, is find boats as soon as the image is delivered. So we tend to receive these images from NASA and the European Space Agency about 3 to 4 hours after they're taken, and then it takes about 5 minutes for a computer to look through these massive images to find where vessels are. And this is an example of Sentinel-2 images, and specifically here, the size of one of these images, this square, is about the size of the country of Uruguay. And so if you had to find something the size of a car in some cases, or the size of a small house in one of these images, it would take you quite a long time and a lot of attention. You would probably get bored or tired and want to do something else very quickly. But luckily, AI does not get bored or tired. And so it can continue to do this 24/7. And so this is the result. We can zoom in and you could see that this successfully found quite a small vessel with its wake, which would have been very difficult to do if you're just looking at the entire image. So as I mentioned, in a very similar way, we ask humans to do this job first. We say, we give humans a set of images. We say, please go through this image, click on the screen wherever you see a ship. And so once we mark that, what we've done here is we have created the training data that's going to be given to the model. The model's going to learn the patterns and trends that humans identify vessels with. For example, say, well, in this case, a radar image, it's a bright spot on a black background, but it doesn't occur in certain locations. The bright spot isn't there last week, last month, and last year. It's something new, so it's moving and changing. And those sort of associations are learned by the model. We freeze the model, and then we give it new inputs and say, all right, now you've learned it, tell us where the vessels are. And it provides us an output. I'm going to talk really briefly about some things that we're planning to do that you don't see in Skylight today, but also involve AI. I'll go pretty quickly through here because we have one more thing to cover. So it's very possible for AI to not only learn when a ship is fishing at sea, but also identify the differences in different fishing types. Again, if a human expert can do this from the tracks, then we can teach a model to do it. And so in this example, we can see the distinctive patterns of, say, a vessel drifting slowly at sea as squid jigging, or repeatedly crossing along a contour on the seabed as trawling, or repeatedly going over relatively straight lines to set their gear and then go back and recover them as longlining, or forming small loops as pursing. And so since humans can learn to identify those things in these shapes, we can train a model to do that as well. We can use these models to forecast where a vessel is going to go. So it's easy to say that we last knew a vessel was going in this direction at this speed, and say this is where they might appear in the future. But we can also make a model give us an assessment, because we've trained a model on all of this AIS data. We know what vessels tend to do next when they're in a particular part of the world and doing a particular behavior. We have a sense of, okay, after a vessel fishes in this area, it tends to appear. After they cross, after they pass around this cape, they turn northeast and continue on at this speed. So because we've done this model training, we have ways of assessing what is likely to happen next, and we can use that to generate forecasts. And we can also do this in imagery too for completely dark vessels. You can see, we can not only see that a ship is there, but we can tell which direction it's going. And you can even pull out a little more information from it, say, based on the size of the vessel and how large the wake is, what speed it's likely to be going. And so therefore, even for a dark vessel, we might be able to assess this is where it will be in a certain period of time. And we're also working on I think Nazi, I think I need to ask you if you can click that. Thank you. We're working on a chatbot, very similar to ChatGPT, but this one is going to help you answer questions about how to use Skylight, or about the data that you see inside Skylight. It works in other languages, which is one of the amazing things about large language models. And it will also allow you to do some interaction with the platform. So you could describe in plain words rather than finding the right filters or trying to configure things. You might explain a particular type of vessel in a particular location you're looking for, and the model can then, as you're seeing here, apply the filters, take you to that part of the world, and show you the results that you're looking for, and then also help you export that information and potentially do more analysis on it, turn it into charts or graphs or other maps or a custom dashboard, because these models are very flexible, and they've learned, in this case, they've learned from the entire internet. So they have a lot of knowledge and skills at their availability. So they can do a lot of things that we don't even anticipate you wanting to do. They can answer those questions or help you accomplish those things. We want to make sure that it works right. And so we're going to be slowly introducing this. We don't want it to give you incorrect answers or make things up, which happens sometimes with these models. So we want to be very careful with the way we use this, but this is going to give more possibilities for what Skylight's capable of. So next, sorry, there we go. Okay, so I think a question we ask ourselves, and we get asked a lot, is, are we doing a good job? And so to talk a bit about AI models and whether they are good or not, we do need to talk about this idea of true and false positives, true and false negatives. And so in short, a true positive is, say, for a satellite image, is we know that there was a boat there in a given location, like maybe a human clicked on a boat, and so we're certain, right? Yes, that was a ship in that image. And then the model tells you there was a ship in that image, and that's great. That's a true positive. The rest of the image where nothing was going on and no one clicked on anything and it didn't identify a boat, that's a true negative. That's excellent too. So sometimes you will see in the platform, the model has provided you a detection, and usually it's going to be one of our little red icons. There's no AIS associated with it. And you might click it and open it, and you might say, that doesn't look like a boat to me. It looks like a small little cloud, or it looks like the top of a wave, or I know my area and I know that there's a rock or a reef there. And that is a false positive. That happens a lot because one, you know your waters and your area better than the model does. The model has to sort of learn generally what the whole world looks like. So it's not very good at doing specifics sometimes. But it also is very easy sometimes, I think, even to humanize, to confuse something like, say, a wave cap, like a white cap on a wave, with a very small boat going at high speed in some of these images. On the other hand, you might look at an image and you might say, well, I can clearly see that we're very near shore, and I'm looking at the entire image, but I could see that there are other small boats moving around. I could see their wakes. I could see where they're going. And that's a false negative. It means that we missed something, or the model missed something, that you were able to see as a human. And that does typically happen for very small detections, again, where there's a bit of confusion that can occur with other similar looking objects. This doesn't happen so much with like big cargo ships. Those tend to be very easy for the model to learn. It's those confusing, harder cases where the model can get confused. We actually call what you're looking at here, this is called a confusion matrix, which tells you how likely they are to get true and false negatives. And we can use this to evaluate the model, how well it does. So let's look at an example of this with Where's Waldo, or I understand in some countries this is called Where's Wally. But so we're looking for someone with a man with red and white stripes on his shirt, and I think he's got a little cap. And so we need to look through this big confusing image that has a lot of stuff that looks very similar for a person that matches that description. And let's make it more interesting and say, we know he's guilty of IUU fishing, but we know he's somewhere in this image, and so we need to find him. So what we're going to have first, we might have a human tell us, okay, these are the people, these are the men with red and white striped shirts in this image. And so we have 4 candidates, and now the model or the human who's doing this labeling doesn't know which of these guys is a criminal or illegal, like the IUUF, the illegal fisherman. But we know he matches that description. So we need a way to look through this image and future images that look just like this. So we're going to start training a model. So we have to ask ourselves, and this is a decision that we can make and control when we're training the model and deciding what model to put into Skylight. Do we want to be correct most of the time, or even all of the time? But we might miss some of the things that we're looking for. So we want to be certain when the model tells you that there was a ship in an image, it's absolutely correct. But we might miss some things. So it's going to give you a lot of cargo vessels, tanker vessels, really large ships that are easy. And it's not going to give you so many of the hard ones, but you know when you click on something, you're absolutely looking at a boat. So what we should do then is improve what we call precision. And so just introducing these 2 terms, precision being the first. So precision tells you you're going to be correct when you do identify something. What if instead we want to be certain that we're catching most of the stuff we're looking for, but you're going to have to deal with more false positives. You're going to catch things that we didn't mean to catch. So in that image, we want to be certain that we're getting every boat we possibly can. But as a human, you're then going to know, okay, I'm going to click on some of these items, and some of them are going to be waves, rocks, clouds. Then we want to improve recall. Recall meaning like, oh, we find everything that the human labeled. We recall it, we remember it, we find it again in the image. But we're going to have to deal with a lot of false positives. So we can't really do both of these things at the same time either. In some ways, we improve one and we hurt the other. And so we might say, I don't ever want to deal with false positives. I only want to see really high confidence detections. So then what I might do, going back to the original example, if I say, I'm going to make a model that's really good at precision, it's going to find me these two men that were very obvious. But if you remember earlier on, we had 4 men that the human had labeled. And so we're only seeing 2 here right now. Yeah, and so we're missing some of the original stuff that was labeled here, but these are very high confidence. These are certain. I click on these, I'm like, yeah, you did a great job finding these. Meanwhile, I don't know if it missed other things. Now, instead, I might say, I don't ever want to miss any of the vessels, or I don't want to miss any of the striped shirt men in this image. I want to be certain that the model gets them all. And the way to do that, then we improve the recall. And if we improve the recall, we're going to catch all of those 4 original men that the human labeled, but we're also going to get a few false positives. So we have a guy who has a really bad sunburn. We have a guy who's hiding behind a towel, actually 2 of them. We have a guy who's wearing shorts. And so those weren't part of the original description, but they're really close to what the model was trained to look for. So it's presenting you more candidates. It's presenting you everything that is a good candidate, but I have to deal with a few of these other ones, whereas a human, I could say, oh no, that was not what I intended to find here. So all that said, one of the ways to improve both of these things is we need more and more and more data. So whenever we train one of these models, we use thousands of examples. We try to make them really diverse, but they can always be better. And so it helps to have our users provide feedback and give us more insights and increase the size of that data set that lets us go back and retrain the model or tag it to find specific problems. Sometimes the answer to is redefining the model or retraining the model, but sometimes it also makes sense to use some rules with a model that tell it, say, well, we know that there's a rock in these locations, so never show us a boat at those locations. That's a particular example where you can combine a rules approach and an AI approach. So with that, thank you so much for your time. We're going to open it up to questions and discussion because we just covered a whole lot. So thanks again.
We paid Theo for that reaction. Thank you, everyone. Feel free to raise your hand, open your microphone. Also, if you need translations from Spanish to English, I can help with that. Mario?
Yes. Hello. I have a question about the data you use to with human identification. You use like very well trained people to do the job, or you take anyone that can identify the ship, or they have you are very careful with that.
Yeah. So for identifying phishing specifically, we sought out mostly from our own user base. We looked for folks we knew were experts in fisheries and knew how to do the task. And so, we evaluate their background, we interview them, we give them a slight training on how to use our platform. And we also write up a guide that explains this is what we're looking for. These are some tips of what you might see and what resembles particular fishing. So for fishing specifically and types of maritime activity in those tracks, we found it's kind of an unusual task. Like most people have not done something like that. Say like, I'm just looking at lines on a screen and I can tell that something's fishing. It's a pretty rare skill. For looking for ships in an image, we have found that, yes, we can tend to find more people who are capable of doing that with less specialized knowledge. So we can open that up a bit broader, but we still check that they're doing a good job. And one of the ways we do that for both of these cases is we have people on the team internally generate like a test set, or what we call gold questions. And what those do is whenever anyone's doing the task, we slip in some of those gold questions where we are certain of the answer, and that lets us check, are they doing a good job? And if they're not, then we can give them some advice or tips and corrections and things like that. So it is something we take very seriously. We don't just let anyone we find on the internet do the task. Yeah.
Right. And so you let them use also ICE data or like different like satellite data to check if they are right about the detection, or just let them use only one image in the case of ship identification, or the tracks, or only the same thing they are going to use the machine learning, or you allow the humans to get more information and to make completely sure they're right?
Yeah, we for tracks, we allow the human to do a little bit of additional investigation about the vessel, particularly if there's like if there's like an ambiguous case. We do allow them to say, look up the type of vessel, and I think a good example is often you'll see like a pilot boat or a tender. Those do maneuvers that sort of look like fishing, and usually like I would say, having done the task yourself, you're usually looking at the track and you say, this doesn't look quite right. So you already see from the track there's something wrong, and it causes you to go do a little more investigating. Another example is we allow humans to say, you might be looking at the track on our map, and our map's not very specific. So go over to say like Google and look up the location and be like, oh, I can see in the image that there's a platform or a mooring there. That explains. For the imagery, what we do is we give the human the image they're supposed to be labeling, but we also give them additional context so they can go back in time and see what else has occurred in that location before they make a decision. And so that really helps with things that don't move, basically, like rocks and stuff like that. So we allow for additional context because there's always the hope that the model can, even if it doesn't have everything the human had, it can learn a little more insights, a little more nuance. So we want to make sure we're giving it pretty accurate labels.
Perfect. I have another question. I don't know if there is somebody else asking.
Go ahead.
Okay. So what about you give the tracks or the ICE data to the machine learning? You just give them the thousands of lines of ICE data, or you gave them the tracks?
We are giving like decoded AIS messages, but we do it at the message level. So the human is labeling tracks to go a lot faster, honestly, right. Because you'd be labeling millions of messages. But we do label down to the individual AIS message, and then we provide those AIS messages go into the model more or less raw. The reason for that is that it lets us detect fishing in close to real time. Like we don't have to wait and do processing and make a track and things like that. The model that we use that allows us to do that now is actually very similar to ChatGPT. It's the same architecture. It's a for those of you who want to hear that, it is a large pre-trained transformer. That's the type of model it is. But what that means is it's a very, very huge model, and so it can handle that volume of data very quickly.
Thank you.
Yeah.
Okay. Any other questions? Yeah. Agus.
Hello, everybody. I just want to know if you have performed some tests on the development of the AI model, how effective it is when you confront to positive and negative errors. Have you evaluated the model?
Yeah, so for AIS phishing detection, we hit about 70 to 75% accuracy by the model. And that seems to be about, so when you're training, you can kind of see over time how well the model does, because you know all the right answers. You say like, how good is it doing? And so you give it 1,000 chances to keep learning. And so, and the score improves as it starts to learn, as it corrects itself. But at a certain point, it does what we call converging. We see it stops improving, and that's because that's as good as a human could do, or we had 20 humans do this job, and sometimes they disagree, and so you hit a ceiling of how well it can do. So about 75% accuracy for the fishing, and then for the imagery, I have a little bit of a different answer, because we've talked about precision and recall. One of the things we can control is confidence. So the model tells us how certain it is that it's looking at a boat, and what we do is we tend to set a filter. So we say, only show users times when you are 90% confident or higher. And so that's the level we've set. If we turn down that confidence level, if we say, oh, you could be 80% confident, what then you end up seeing is more false positives in the mix, but you might pick up other things that you were looking for. So we kind of arrive at that confidence level by, again, like we have a very distinct score. We say, like, what's the best you can do on precision and recall at the same time? And then you get an answer that says, like, yeah, if you set it to 91%, I will do as good as I can on both of them at the same time. And so that's how we arrive at that.
Thank you very much.
Yeah.
Thank you for your question. Just to add a piece of context on that, when we had our experts training the model for the fishing activity detection, our experts only agree 85% of the time, right? Because we as human cannot, if we don't see the activity, we cannot be 100% sure that this is happening. So asking all the experts about all the activities, sampling, they only agree on 85%. So if the model was absolutely perfect, we will aiming at 85%. And at this point, as Joe said, we are doing a pretty good job. I'd say we are hitting 70 to 75% of that 85, right? Any other questions? Okay, I will let you ask more questions, but we have 3 more minutes, so I want to take these minutes and ask for your help here. As we said before, we improve our models. This is part of our culture in our organization. We always want to improve, we want to do better. So this also applies to these sessions. These training sessions are evolving over time, and we certainly can use your feedback. So if you can scan this QR code, I will also paste, let me paste it, okay, here on the chat. So you can open the feedback form. These are maybe 5, 6 questions. It shouldn't take you more than 3 minutes, but we do appreciate your answers to improve these sessions. This has helped us, and we certainly adapt the sessions. And one of the things we heard from our users is that having one session covering everything was overwhelming. So we decided to split these sessions in a basic training and then have additional deep dives and additional updates sessions. So this is part of our users were asking from us. And if you have additional requests, we're happy to hear that. And yeah, I will put this slide on, and so you have our contacts in case you have additional questions. And please feel free to ask more questions. We stay around. Mario, please go ahead.
Oh, thank you for the class. So I have another question. What about the ship, the detection? Is it about also 85% the performance?
That's a really good question. So I actually don't remember the maximum. So the score that we use that combines, just for everyone, the score that we use that combines precision and recall together is called the F1 score. Okay. And we try to maximize the F1 score. And I actually don't know when we maximize F1 what our accuracy ends up being. So I'm very sorry. I can get back to you on that, but I don't know off the top of my head.
And I have another question. So if when you do the actually the accuracy, when you know exactly what events are real for real, so that subset is too small to train with that, and
yeah. So we have a training set. The training sets we build for ship detection end up being about 10,000 ships or more that are found by humans. We use that to train the model. And with any AI, what tends to happen is that you use something like 7,500 of those, and then you save a section of them. You call that your test set. And so you train the model on those. You do this because, like a person memorizing a test, where you're like taking a test in school, you're like, I'm just going to learn the answers. I'm not really going to learn the information. A model can do that sometimes, and it's called overfitting, and it just means that it's just memorizing exactly what you show it. That's bad, because then you show it other stuff in the real world, and it hasn't actually learned. It's only learned exactly what it's been taught. So you hold out a test set, and then you evaluate it. Mario, I'm sorry if I think I see you nodding like you know some of this, so I'm just making sure, giving all the context. Okay.
That's good. Well, that's good to
okay. Yeah. So then what we also do is, once the model's trained, we use the training set, and then we use the test set to score it. And then once the model is out and it's in Skylight as you see it, we then actually run another set of tests. So we'll start, we get all of the detections that Skylight's finding. We choose them at random, we usually do about 1,000 or 2,000. And then we have humans look at those again. And now that you have the outputs of this system kind of in the real world, we then like score it again and see how well it's doing. And that tends to hit about 85% accuracy as well, where we say like the model was correct 85% of the time. When a human then looked at its results, 85 times it was a boat, 15 times it was something else. So yeah, we do a lot of rounds of testing.
Thank you. Thank you.
Yeah.
Okay. Any other question? Okay. So you have our contacts here. We are always available to give you more data, more information. We can follow up this conversation later. But I'm going to wrap up this session here for today. Thank you so much, everyone, for joining, for staying, for asking questions. It was great to have you and to see your interest in learning even more. This is inspiring, and thank you so much for being there. And let's stay in touch. Have a nice day, a nice afternoon. Yeah, a nice one, whatever that is. Bye, everyone.
Thank you very much.
Thank you.
Thanks, Natalie. Bye.